Hi everyone, today what we're looking at is we're looking at the exact values table. So, the table of exact values is derived from a series of triangles that have angles that we know. So one of the triangles is a 45, 45, 90 right angled triangle. And there are two sides of length 1. What is the length of the hypotenuse? Well, that's root 2. Now, what happens though is that with using the two triangles, so which I will create for you now. Now, the two triangles, when you use them, allow you to create some particularly interesting ratios between sides. And as part of that, we can then use that to create a table of what we call exact values. And then we can use that to solve a lot of problems involving trig and triangles pretty quickly. So in this case here, I have a 90-degree angle here, and these side lengths are both 1. What sort of triangle is this? It's a right angle triangle, but what's the other special property of that triangle? It's an isosceles triangle. And what does that tell you about these two angles here and here? These sides are the same, therefore the angles are also the same. They are equal. So if I've got 90 degrees here, how many degrees do I have left to go over the rest? Well, I've only got 45. Now, how long is this side here, the unknown side, the hypotenuse? And it's not 1 because this is 1 and this is 1. Use your Pythag. How long is the hypotenuse in this example here? It is indeed root 2. Because 1 squared plus 1 squared equals 2, and that means, so it's the square root of 2. Now that means that if I was to talk about, well, what is the sine of 45? Any 45. Either of the 45s, it's fine. It's going to be equal to 1 on root 2. What about the cos of 45? So if I'm going from here, it's also going to be 1 on root 2. Now, those of you who remember back to earlier in the year when I told you never put a surd on the bottom of a fraction, how can I change these 1 on root 2 so that they are something a little bit more aesthetically pleasing? Yeah, so I multiply by root 2 on 2, root 2 on root 2. So that 1 on root 2 times becomes root 2 on 2. Now, this conversion is important for how to remember the shortcut. All right? Now, what I also have is another triangle. And this time, the triangle is going to be it's going to be a very different sort of triangle. So I'm going to draw a triangle where all three sides are the same length. And what is that going to do about the angles inside that triangle? What are the angles inside this triangle? All three sides are the same length. They're all going to be equal to 60. Now, what I'm going to do is for this particular triangle, I'm going to say that all sides are length 2. This will become useful in a moment because what I'm going to do is I'm now going to cut my triangle in half. All right, so if I take a straight line and I draw a line straight down the middle of it. All right, I cut that line in half. What have I now created? I've created 2 right-angled triangles. That's 90. That's 90. What is this angle up in here now? I've cut 60 in half. So now this angle here is only 30. What length have I created down here? I've created an angle of length 1. That means if I was to measure this new triangle, if I get rid of everything that's not everything else about this triangle and I just worry about my new half triangle, how long is that new side? How long is this side here? All right, it's going to be equal to root 3. So it's going to be equal to 1 squared plus question mark squared equals 2 squared. So that's going to be equal, so question mark squared is equal to 4 minus 1. That means the question mark is equal to the square root of 3. Cool, so we've got that. So if this is my reference angle, that I've got here, so we're going to talk about this one first. So theta is 60. So what is the sine of 60? Looking at my diagram, what do I have? I have root 3 on 2 because remember, it's opposite over hypotenuse. Opposite is root 3. And the hypotenuse is 2. What about the cos of 60? It's 1 on 2. Now, if I change my mind and I choose my other angle as my reference angle, what's the sine of 30? It's a half because I'm going opposite over hypotenuse. And then what about the cos of 30? It is root 3 on 2. If you look at the sine and cos values of 30 and 60 and 45, what do you notice about how I've expressed them all? How have they been expressed? Fractions, but what's the common fraction? They've all got a denominator of 2. All right, and that leads me to my next trick. So what I'm going to do is I'm going to draw up probably gonna need a little bit longer. I'm horrible at writing these because I actually need. Yeah. Oh. I knew I was going to run out and needed extra ones. All right. Actually, I've missed multiples. Yay! Oh, you're smart. So what I'm going to do here is I've got a table of values that I'm going to say theta. In here I'm going to put the sine of theta, the cos of theta, the tan of theta, and I'm going to ignore the rest of it because I've drawn way too long lines. Now, the values that we care about are the values that we got out of our two triangles. We have 30, we have 45, and we have 60. I have two other angles above and below that I need to be able to know. 0 and 90. Now, the cool thing is that everything is expressed as a square root of 2. 30 was a 1 on, yeah, so 30 was 1 on 2. 45 was root 2 on 2. 30 was root 3 on 2. So I've got the angle here, I've got sine, cos, and tan of those angles, and I just drew way too long lines. Look at this 1. Now the square root of 1 is 1. So, but if I just put a square root in there, what do you notice about the square roots? They're in ascending order. Following my logic, what number should go here? So it's the square root of 0 over 2. And what about this number down here? Now, someone has just said root 4 on 2. What's root 4? 2. What's 2 on 2? Now, if you were paying attention, you would also notice that the cos of 30 was root 3 on 2. The cos of 45 was root 2 on 2. The cos of 60 was 1 on 2, so root 1 on 2. Now this one goes in descending order. So up here we would put root 4 on 2, and down here we would put root 0 on 2. So, if you remember the angles that you need to care about, 0, 30, 45, 60, and 90, you can go sine of 0, so sine of 0 is 0 on 2, 1 on 2, root 2 on 2, root 3 on 2, root 4 on 2. Then simplify what you already know. Cos is the opposite. It just runs in the opposite direction. Tan is interesting. What is the relationship between sine and cos with tan? Sine over cos does indeed equal tan. Thank you. That means that I can divide sine by cos to get the tan of that angle. Now, so this is 0. So 0 divided by something is 0. 30, so that's a half divided by root 3 on 2. So that's a half divided by root 3 on 2. When I simplify, when I do a fraction divided by another fraction, what can I do instead? I can instead multiply by the reciprocal. So I can now change this to 2 on root 3. What happens to the 2's? They cancel down. So simplified, it's 1 on root 3. Now, and there you go, gold star. You've said simplified, it's 1 on root 3, which then, because you can't have a root on the bottom, you would multiply the top and bottom by the square root of 3, and that gives us our new value here, an exact value of root 3 on 3. Root 2 on 2 divided by root 2 on 2. Well, that's itself divided by itself. So that's 1. This one here, root 3 on 2 divided by a half. So that's root 3 on 2 divided by 1 on 2, which is the same as multiplying by the reciprocal. So I'm just going to be multiplying by 2, which then cancels out the 2 and the 2, and I'm left with the value here of root 3. And then the last one, 0 on 2 is 0. So what is 1 divided by 0? Undefined. So it's a divide by 0 error. That's going to become important later when we talk about graphing these things. So, all you need to remember to create this table by hand, without much memorization, is the angles that we care about, and then by putting sine in the order of 0, root 1, root 2, root 3, root 4, all over 2. Cos is going the opposite direction, so it starts at 4, 3, 2, 1, 0, and then tan is sine divided by cos. If you can remember that, then you can create that table straight away, and you don't need to actually memorize what is sine of 30. Well, I can go back and I can create the table again, and all of a sudden, I've got a lot of work. I've got it all done. Because if I'm going to ask you for the exact value of one thing, I'm probably going to ask you the exact value of a few other things at the same time. So just quickly, these are all in degrees. And what's that wonderful new measuring system that I've been trying to get you guys to think about? Yep, radians. So this is degrees, radians. So this is 0 radians, 30 is 30 degrees, how many radians? Gonna need something a little bit more specific than that. It's pi on 6. Pi on 45 in radians is pi on 4. 60 is pi on 3. And 90 is pi on 2. So now if I ask you what is the sine of pi on 6, well, the answer is a half, 0.5. So when you go through onto your CAS and you start playing with these, when you play with these, again, we'll set our CAS into radians, not gradients or anything else. And we do cos of pi on 6. We get this answer here in decimals. Now, if I set my calculator standard and I do the same thing, it has an exact answer. All right. If I am working with angles that are fractions of pi, it can, in radians, it can probably give me an exact value. As long as I'm working with fractions of pi, it can give me, in most cases, exact values, unless it's too small. Because, yeah, that's pretty small. Well, close to 1. Pi on 8. Root 2 plus 2. So it's the square root of root 2 plus 2 all divided by 2. So they get a little weird and they get a little messy. But the important ones are 2, 3, 4, and 6. Other ones I'm not so fussed about. And if you do it on your CAS and it produces something that you're not expecting, like that one there, tap the answer, press the button, and it will convert it to a decimal. Otherwise, you leave it in exact value, which is the cos of pi on 7. All right, not every one of these will have an exact surd or root value. So sometimes you just have to need to leave things alone like that.